College voor promoties.
Meneer de promovendus, het college voor promoties van deze universiteit, door ons vertegenwoordigd, heeft kennis genomen van uw proefschrift met bijgevoegde stellingen en is bereid u deze te horen verdedigen. Ik verzoek u plaats te nemen. U kunt gaan zitten. Is er iemand uit het publiek die met de promovendus van gedachten wenst te wisselen? Ik constateer dat dat niet het geval is. And then we will start our opposition with the first opponent. And a special welcome to Professor Walde from the ETH Zurich, who is the first opponent today. Professor Walde, you can start your opposition.
Thank you. Esteemed candidate, it was a pleasure for me to read your thesis and go through the details of your work. I have a couple of questions. The first one is a more general. So what is, in your opinion, the biggest achievement of yourself during the last years while you were performing your experimental work?
Highly learned opponent, thank you for your kind words and your question. I'm not sure if you mean on my personal...
Yes, your personal,
Okay.
your work. What is the biggest success, so to say?
I would say that the biggest success is becoming a relatively independent researcher. So I have managed to made a project that was good enough to write a thesis and will also produce some papers. So I think that's one of the main goals of PhD studies, to become an independent researcher who can do their own research.
Okay. So concerning the molecules you were using, there was some design behind the structures.
Mm-hmm.
Can you explain to me why, for example, in the aromatic ring, you had two aromatic rings in your components. The first one has two sulfhydryl groups, and there was another aromatic ring which was para-connected to an amine. Can you explain me in the second aromatic ring why this position was meta actually and not para, for example?
This was mainly due to synthetic reasons, so it was simpler to synthesize this compound, but also the other component could be synthesized to see the influence of the structure on the assembly of these molecules, but mostly due to synthetic reasons.
Okay. So during your work, you also used additives like alcohol.
Yeah.
And you got some success with respect to vesicle formation.
Mm-hmm.
Do you understand why the presence of these alcohols have a positive effect on this vesicle formation?
So our main hypothesis about this question is that alcohols act as simple amphiphilic molecules. So they themselves have a hydrophilic and hydrophobic part, and then they can go between molecules within self-assemblies, and they can change the packing of these molecules. And this packing then results in different probability of having different structures formed. So for example, if you look at molecules packing together, maybe the head groups are too big or too small, but then if alcohol molecules squeeze between, they can change this packing of molecules. And this then results in different structures formed.
Okay. So which of the alcohols were actually the most promising for vesicle formation?
For vesicle formation, it was isopropanol.
Isopropanol.
Yes, in low percentages, around 5 to 10%. And with those, we actually saw, so to say, improved structures compared to pure libraries prepared in bored buffer. So they looked more like vesicular structures.
Mm-hmm. And what about, I think I remember also methanol. You used 50% methanol in some cases with some molecules.
In that case, actually, we did not see the formation of vesicles, but we observed the formation of amorphous aggregates, which had, so to say, flaky structures. So it looked sort of like precipitates, but the thing is that in that case we observed the self-replicating properties, which we could not observe when we had formation of the vesicles, which means that one excluded the other. Our initial goal was to have these things simultaneously, but the thing was that we either formed vesicles or we had self-replicating properties of self-replicating entities, which in with different co-solvents were actually different oligomers. So we had either tetramers or pentamers or hexamers.
Okay. On page 79, you described the formation of vesicles from compound 1.
Yep.
And there you use 10% methanol and also borate buffer, pH 8.5. Is this pH important? Is it important to have a borate buffer?
Well, the buffer itself has influence on the self-assembly, but the most important thing is that we have slightly basic conditions so that we can have free thiolates in the solution, which then enable or fasten or make the exchange of disulfides faster.
Okay. So with respect to the whole chemistry where you have thiols and you form disulfides, could you imagine some other chemistries for these combinatorial libraries to maybe possibly achieve a similar kind of oligomers?
Yeah, I mean, the nature of exchange could be different. We could simply replace sulfur by selenium and then have diselenide exchange. But I think the synthetic routes would be a bit harder for that. But we could also have hydrogen exchange or any other dynamic combinatorial chemistry that allows us the exchange of...
So which one, for example? Chemistry.
Sorry?
You mentioned also another chemistry, for getting this, let's say, kind of library. If you start with library of compounds and make this, let's say, kind of oligomers. So which type of bond formation chemistries, alternative to the thiol, would be possible? I think you mentioned in the introduction.
Well, one option is diselenide exchange,
yeah.
And the other would be hydrogen exchange.
Yeah, or maybe also the aldehydes
yeah.
with the amine to make the imine. That's good.
Imine formation, yes, indeed.
So would this be a possibility, if one would continue with this work, to use instead of the thiols this type of chemistry? Do you think that this would be possible?
Well, the design would be a bit different because in that case we would have two parts of amphiphilic molecule coming together and then forming the super amphiphile, while in this case we have only one type of molecule which forms oligomers, and then these different oligomers can assemble in different ways. So it would be a different approach, I think.
Thank you. So another question is, what is this packing parameter concept with respect to this vesicle formation or micelle formation? Can you briefly explain?
Well, packing parameter briefly shows us what kind of aggregates we can form from amphiphiles if we look at the shape of the molecules that are assembling, which says that we have a head group and a tail group, and then depending on the size and shape of these head and tail groups, we can predict what kind of aggregates are most likely to form in water solutions.
But do you think that's really a prediction is possible?
Prediction for this is generally very hard because head groups have to be looked at in the aggregated form, first of all. But in this case, this was used only as a guideline, and it cannot really tell us what aggregates we can expect. Because, first of all, we look at the shape of amphiphilic molecule as a monomer, and molecules that assemble in this case are oligomers. So already oligomers have different packing parameters from the monomer units, so they cannot be applied directly. But in this case, we used it only as a guideline, so it cannot be applied directly, which means that we can change the shape of the molecule by increasing or decreasing the length of hydrophilic chain or increasing the size of hydrophobic group, and then we can see what kind of aggregates we form. So we can have a guideline in which direction we should go, but it cannot be applied directly, definitely.
Mm-hmm. Okay. Thank you.
Thank you very much for your opposition, and we will go to Professor Marink from this university for the next opposition.
Dank u wel, meneer de voorzitter. Esteemed candidate, also my compliments for this beautiful work. It's amazing how many experiments you have done, and it's fascinating to see the kind of structures that are formed in these dynamic combinatorial libraries. However, I have the impression that a lot of it is still based on trial and error. You try to change the conditions and then see what is happening and analyze this, and then, of course, try to come up with an understanding of why things are happening, but mostly this seems to be still quite difficult. And so it was already discussed, this packing parameter concept is an attempt to explain that, but we just heard, and I think you agree, that actually it's not applicable in this case. Could you again confirm that?
Hooggelerde opponent, thank you very much for your nice words and question. Yes, I would definitely agree with this, with you, that packing parameter cannot be applied directly here, but also I think in this case the whole research was more of an exploratory approach, so we were not quite sure what to expect, and then when we set up new libraries we found interesting outcomes, so we were following the most interesting directions, which meant that it wasn't really like we had a clear structure in mind, and then we tested if we can achieve that, but we had some guidelines from this basic principle.
Okay. Okay, but let's move to chapter 2, the formation of the vesicles, which I find quite intriguing. This is an important way of forming compartments. So let's have a look at figure 2.5 on page 32. There, this is actually one of the few images I found in your thesis where there is some packing of your molecules being shown. In this case, this is a micellar structure, which I think is the initial aggregates that are formed. Is that correct?
Yes.
Okay. However, I'm trying to figure out how from this micellar structure you eventually end up with vesicles. And if I understand correctly, you assume that the vesicles are mainly composed of tetrameric structures. So can you explain me how it is possible that inside these micelles only tetrameric structures are being formed? That first, and then second, how these tetrameric aggregates, how they pack or are able to pack inside a lamellar type of structure?
So in this case, the micelles indeed show the initial aggregation, which is just for monomer, and that we presume that by this packing in micelles, we actually enable the formation of bigger oligomers. So oligomers that would usually form from this kind of structures would be mostly trimers and tetramers, which are entropically most favored. But we also form different bigger oligomers. And then they indeed form different structures. So if we don't use any co-solvents, or if we don't increase temperature or change parameters during our experiments, they form also nanosheets, they form sponge phases, and...
Okay, yeah, that I understand. But so you say inside these micelles, you already, the deformation of all these different sized oligomers is initiated, so also the tetramers. So let's focus on the tetramers. Are they cyclic tetramers or linear tetramers, or?
Yes, they are cyclic tetramers. We can prove that.
Cyclic tetramers. So then I have a very hard time to envision how such a cyclic tetramer, which has basically a hydrophobic core surrounded by hydrophilic tails, how that could end up packing into a lamellar structure that you need to form a vesicle.
Yes, so we tried to test this by computational methods, but with not much success. So we had two ways of imagining how this happens. So one is that we have a tetramer which forms a monolayer, or tetramers which forms bilayers. So in one case you have tetramer with hydrophobic parts together and then tails pointing outwards, and then they form lamellar structures.
But how can that form? Because that it is inherently a cylindrical type of aggregate, right? So you would expect it to form worm-like micelles or fibers or something.
Well, cylindrical amphiphiles also can form in lamellar structures, especially if we have some flexibility in the aromatic part, in the hydrophobic part.
Okay, well, I think it would have helped if you would have drawn some of these ideas, how these molecules then would pack inside all these fascinating structures. All right, let's move to one of your propositions, if there's still time for proposition. Yes, maybe one of your paranymphs can read out proposition number 4.
Amphiphiles both love and hate water. The same relationship is common for many PhD students and their research.
Thank you. So amphiphiles love and hate water. I guess the hating part comes from the hydrophobic tails that don't like to mix with water. Can you explain to me what happens if you put an oil droplet on a water surface?
Well, it will not mix with water, so it will either make a layer on top of water, or it will disperse into small droplets.
It spreads on top of the water.
Yeah.
So actually this means that oil quite likes to interact with water.
But it likes to interact with itself more.
No, actually it likes to interact with water more. It's the water that doesn't like to interact with the oil.
Okay.
So if we then look at the PhD student and the research, it's probably not you not liking aspects of the research, but probably the research not liking you, or how should I interpret this?
Yeah, I guess that's called bad luck. Or...
Okay, is there more time?
There is still time for the question, yes.
Still time, okay, let's then go to a bit of a more ethical question, which is of course also, is important if you deal with building synthetic life. And this is, if I look at the introduction, it's called Towards Synthetic Living Systems. Mm-hmm. So the first question is actually, did you succeed in building a living system?
No.
No, okay. But you tried, right? And so you have tried many conditions. So what if suddenly in one of the trials you would have actually ended up with something that you could call synthetic life? I mean, you would have been very happy, right? Because this is what the field is probably after.
I think the chances for that were quite low, actually. Even from the beginning, I was aware of that. But the thing is that we were not in this project itself trying to achieve living systems, but the overall goal of our group's research is to achieve that. And this is one of the projects in which we try to capture some properties that living systems have. And once you build systems that have this kind of properties, you can combine different systems and then bring more and more properties together until at one point you have all essential properties that are necessary to have a living system, but at that point we still cannot, at this point we cannot know if this will be a living system or not.
No, okay, but you're working as a team, and of course, eventually, hopefully, you can achieve this. But still, I think you need to think about the ethical implications of it. So one day, you or the group that you work in might achieve this, and then how are you going to sell this to the public?
Oh. Well, I guess this will raise a lot of discussions then. But important thing would be that if we do achieve a living system, then we would be able to figure out essential properties of living systems and could understand the origin of life on Earth better. But this would, of course, raise a lot of ethical.
Yeah, so there might be people that think you are a dangerous fool in playing with these systems that might get out of control, right?
But then it would need to be explained very well that this does not raise some kind of threat to the life, for example, to the life that we know, because it's based on completely different chemistry that cannot interact with each other.
Okay, thank you very much. I give the word back.
Thank you very much. And the opposition will be continued by Dr. Stewart from this university.
Esteemed candidate, first of all, my congratulations with this thesis. It's a very brave piece of work in a complete new area of dynamic combinatorial chemistry. And of course, I also like the enormous amount of electron microscopy in this booklet. That pleases me a lot. When I was reading your thesis, I realized that there is a contradiction between the dynamic combinatorial chemistry and the classic surfactant chemistry. Because here you rely completely on self-assembly of molecules, but we know from the classical surfactant chemistry that biophysics, that there is no such thing as self-assembly of vesicles, because you always need to put in energy. And of course, I realize that practically in your setup, this is very difficult to achieve. But how do you could overcome this problem? Yeah, because in many cases there you find just aggregates, not really vesicle-like, but sediments. But these could well be forming really nice structures if you put more energy in it to form them. How would that be possible in this setup of you?
Zerheler, the opponent, thank you very much for your kind words and the question. So in this case, I guess you referred to difference between steering and not steering, which means that in most of the cases we indeed observe formation of vesicular structures only when we steer the samples or shake them or have additional ways of putting energy in. But this also shows, so I'm not quite sure what your exact point is.
Well, in many cases, if I make vesicles, which I do more or less on a daily basis, if I just take a phospholipid and put it in water and do nothing, nothing will happen. And in many cases, even stirring is not enough to get an amphiphile to form a vesicle. Yeah, because you need freeze and thaw or you need sonication, so you need to put in energy there to make these structures. And here, of course, I see that it works, yeah, because many nice vesicles are formed and also other structures. But in many cases, you don't see that. You just see sedimentation or no formation at all. And maybe these objects, they still could form really nice structures. But that is something you miss in this case. Yeah, would it be wise to, before you make a sample, just homogenize your sample and sonicate it, freeze and thaw, or put in more energy to see if it does form something? Because in most cases, even if you see no vesicles, you can still identify larger macrocycles.
Yes, so for this I would say that if vesicles are not formed in non-shaken samples, we are not, or they are, we are not very much concerned with that because we are only interested in conditions in which they do form. So if we have to provide energy to form them, then why not?
Yeah, but that's typically a situation that you normally don't have. So that's, of course, the contradiction between the two fields. Okay. Then, when I first started and I looked at page 32 and looked at your compound 1, I couldn't see the amphiphyll there. Of course, you show in the picture there that clearly micelles are formed. But I was wondering, would it be helpful to measure a CMC, for instance, or to measure any other aggregation parameters, like dynamics of the micelle? Could that help at least to understand your system?
Yes, indeed, that would help us a lot, but for some reason we did not perform these experiments. But measuring CMC, for example, would help us to see the amount of building block which is left free in solution, which is in monomer state, and also which is trapped actually in vesicles, in micelles, sorry. But just from cryo-TEM and DLS, we were already quite sure that we do form micelles, so we didn't further test.
Yeah, but you assume, and that's what you write on page 31, that the reaction takes place in the micelle, but as long as you don't know what the partition is between monomers and micelle, I think that is an assumption that you cannot make at this point. And also, and I think then, if you know that and you go towards the development of your system, and that is what Professor Moying said, how can you see the change from micelle to vesicle? And so there must also be a change in CMC during your reaction, because there must be, and with that you get probably more insight in your reaction. Do you think that's a good way to go in this field, or?
I think that's definitely some additional experiments that could provide us with a lot of information about the system, because if we followed, for example, CMC or even just cryo-TM evolution over time, we could have more insight into how this aggregates form. But we do see that in early stages, if we perform cryo-TM measurements, we only observe either micelles or irregular aggregates, while with time, as the sample ages, we do observe more structured aggregates.
Okay.
So we already have some insight into that, but of course additional experiments would help us with that.
Okay. Mr. Chairman,
You're still allowed to have another question.
one more question? Okay. Then at some point in your thesis, you, and I think it was, let me quickly check, on page 166, you put some empty pictures there. And with that, I think you want to prove that there was no aggregates formed. This gives the suggestion by putting the picture that this is sort of a proof. And of course, with electron microscopy, it's very easy to see the things that are there, but the things that are not there, of course, you never know. And by putting the picture here, you give the feeling that this is sort of a proof.
Okay.
Wouldn't it be better to leave the picture out of this?
Yeah, indeed, I agree that this picture maybe should have been left out, because by not seeing stuff in TM, we cannot say that they are not there. It's just that we didn't observe them. So, yeah, indeed.
Yeah, and I think in general the words would do enough, because now it assumes, or at least the non-expert readers, they would believe that you have proven with the picture that it is there, but or nothing is there, but yeah, that's something you can't, of course.
I just felt that, like, if I say that nothing was observed, also to show the pictures that show that we didn't see anything. But I am aware that this is not a proof that the things are not there.
Okay, thank you very much. I'll give the word back to the fourth.
Then the opposition will be continued by Professor Cerci of this university.
Esteemed candidate, in reading this work, it strikes me that a central problem in origin of life research generally is finding an agreed upon set of boundary conditions with which to define life. Not necessarily a precise definition of life, but in fact just boundary conditions for starting to guide yourself towards a definition. And this is really captured in, for example, the absurdity of trying to define prebiotic conditions for life without actually knowing when life formed, right? You need to know the exact moment when it happened in order to define pre and post-biotic, right? So this is a boundary condition problem, as I view it. Now, in this thesis, you actually spend a fair bit of time spread throughout different chapters in the Stellingen, putting forward your own boundary conditions. And one of these you discuss, I think a central theme actually, is that you keep coming back to Darwinian evolution. And you say that, for example, and this is a common thread in defining these boundary conditions, is you pick somebody else's argument and then you show some absurd example of this, right? So the reductio ad absurdum argument. And in your boundary condition argument, you say that mules don't undergo Darwinian evolution because they cannot reproduce. Now, I have successfully reproduced twice, but I did so with another human being. So does it matter if I'm a horse or if I'm a donkey or if a frog and a bird come together to reproduce? Why does that preclude Darwinian evolution? So I guess what I'm asking here is, what is your definition of self when you talk about self-replication and reproduction? Because I would argue that if you exclude mules from Darwinian evolution, you have to exclude me, because my children did not bud off of my back, or I did not divide into two humans, right? It required two humans coming together to do that, two separate entities.
Highly learned opponent, thank you for kind words and interesting question. I believe that the thing is, for example, with the example of mules, is that at this point they cannot reproduce anymore even if they have another of the same species. So in other species which are able to reproduce, maybe it can be by itself or it can be in couple with another one.
So then...
They're sort of dead end.
Right, but why then is a species boundary not just an arbitrary boundary condition that you're applying? So let me take, for example, a boundary condition that I think many people apply is that living systems are always far from equilibrium, or they're, however you like to characterize that. And that means that they require the constant input and dissipation of energy. Now, if you're going to make artificial life in a laboratory, oftentimes you hold a system out of equilibrium artificially, if you like, right? So there's a syringe pump, or there's a person adding or subtracting things to this system, right? So then the system could never truly be self-replicating or undergo Darwinian evolution if you put a similar species boundary on that experiment.
Okay. At this point, I think that the system might still be capable of reproduction. It just needs external energy, like also any known species needs. So it needs metabolism to keep itself away from equilibrium. But if it doesn't have, so these are the necessary traits of life. It has to be able to keep itself far from equilibrium. So it has to be able to produce, to take energy from environment and keep it for itself, to stay in itself. But if it cannot reproduce anymore, then it doesn't mean it's not alive, but it's not, it's very debatable, because, I mean, mules are obviously alive, but they do not fall under the definition of life, one of the most common ones, which was set up by NASA. So what I wanted to point out there, that life is actually hard to define, because if you try to define and just put the properties that life has to have, you can still exclude obviously living systems. So in this definition, mules are obviously excluded because they cannot continue the Darwinian evolution, but they are also obviously alive, so they do not fall within the definition of life as it is in that case.
But then my question is, why can't they undergo Darwinian evolution? So how do you not know that a horse looks at a donkey and says, and says, boy, that's a nice donkey, I'd like to make a mule. And then they make a mule, and that mule has some attractive characteristic that then drives other horses to find other mules, other donkeys to make more mules, right? In other words, does it have to be do we have to put this arbitrary species boundary condition on our definition of life? Does it have to be one species reproducing with itself in order to satisfy the conditions of Darwinian evolution? And I guess one of your stellings sort of addresses this, if I could. Right, so maybe you could ask a Paranymph to read stelling 2.
The evolutionary advantage that mutation can contribute to a species needs to be understood at the overall population level, not only as direct advantage for an individual. Simply by increasing the variety, a chance of a single threat eliminating the whole population decreases.
So I think that actually captures why a mule, in my opinion, does undergo Darwinian evolution. Because it doesn't really matter if mules are reproducing with themselves, it just matters that they propagate and reproduce in some general respect. So maybe mules represent a mutation that occurs not just in the species of horses and not just in the species of donkeys, but in the whole biosphere or in the whole definition of life. I mean, do you disagree with that?
I think I would agree with that because it basically means that mules need other species to undergo their own evolution. So they still can evolve, but they just do it through other species because they don't reproduce themselves.
So then, very pointedly, do they undergo Darwinian evolution?
Indeed, yes.
They do. Okay. Do I have time for another question, or?
I have time for another question.
So I just have a general question about this chicken and the egg problem of compartmentalization versus the self-replication of, for example, RNA. And you state in here very pointedly that figuring out which one came first is a central problem, if I understand correctly. And if indeed I understood what you wrote, you want to have two self-assembling or self-reproducing systems, self-replicating systems, one of which tends to form vesicles and one of which tends to form something else, something, DNA-like, I guess, or RNA-like. And so in the compounds that you showed, I sort of put them into two categories. One is the amphiphile, where you have what I call non-specific interactions, meaning they're not really directional. And this is, here energetically. And then the other one, you have directional interactions. And energetically, this is much lower, right? So it's much more stable to have these directional interactions like you have an oligopeptide, for example. And so is this a solvable problem? Because if I have a system that has really specific directional interactions interacting with another system that assembles by these very higher in energy and less specific interactions, it seems like they'll always commingle, yet you'll always have some of the species that has the directional and specific interactions also propagating on their own, which seems to be, if I understood correctly what you wrote, what you observed in all cases when you mix these together. And so I guess two-part question is, one is this a solvable problem just from a thermodynamic standpoint, or are you always going to fall into this, I guess, entropic trap because of this differentiation between specific and non-specific interactions? And then secondly, can you actually make a micelle out of something that has specific interactions that can compete at the same level of non-covalent bond energy as an oligopeptide?
Okay, in this case, the interactions within peptidic building blocks were indeed stronger, and then they just took over the assembly paths and included amphiphilic building blocks within their structures. But what we were trying to show is if we can actually, to separate their own and have one of those initiate the growth of the others. So it was only to see if, so I think the main strategy would be to have interactions as different as possible, so that the self-replicating entity that is supposed to initiate the growth of amphiphilic molecules would not interact with amphiphilic molecules themselves. That would be, I think, a valid strategy to go towards this goal.
And I guess my question is, do you think that this is energetically feasible, seeing as how you're limited to a single solvent to solubilize both systems, so they have to have some similarities? And I'm getting looked at by the chair, so I think my time is almost up.
Well, we could also use different dynamic combinatorial chemistries for two sets of replicating molecules. So one dynamic combinatorial chemistry for amphiphilic building blocks, and the other one, for example, the one that carries the information. And then if those two cannot interact with each other, so if they're just simply not interacting, we would achieve that, I guess.
Okay, thank you.
Thank you very much. And I give the floor to Dr. Witte of this university for a short opposition.
Dank u wel, meneer de rector. Dear esteemed candidate, I also would like to congratulate you. And I kind of want to tap into the discussion that was already before in a slightly different angle. But in chapter 3, you describe these tetramers, pentamers, and higher order structures. And you show that some of them form fibers, and those kind of self-replicate. And then you also show that some other structures form micelles. And so my angle is more from a mechanistic point of view, because what you write down is like on page 86, you say, unfortunately, none of the self-replicating entities formed compartment and structures. But this is really likely to happen if you look at the mechanism of how you form self-replication. Right, because maybe you should discuss the mechanism a bit of the self-replication and then say, well, how does this match with micelle formation?
Very learned opponent, thank you for kind words and the interesting question. Indeed, in this case, we did not observe the formation of self-replicating vesicular structures, and the difference here is that we assume that the mechanism for their reproduction or replication would be different, because in the case of fibers we have this growth and breakage mechanism where the ends of fibers are catalytic places to form new species, while in the case of vesicles we would have to have a growth and division mechanism in which we have basically two main components, and one is the growth, so we have to initiate the growth of vesicles, and once they become unstable they also have to divide. But this is the thing that is very hard to control, because in living system you have a very complex machinery that controls here, and we were trying to achieve this simply by adjusting physical-chemical conditions. So
yeah, but so now you're reversing it. So I agree with you that this is exactly what is correct. But what you write down is, unfortunately, none of the self-replicating entities formed compartments, which is the other way around, right? The mechanism you have well established is the autocatalytic mechanism, breaking fibers and growing. So that's kind of reversing it. But how are you going to achieve this growth division? Is there a way you can overcome this? Because I think this is a fundamental problem on tackling this, is getting that incorporated into the system.
indeed, that's basically the main challenge of the whole work. So there are ways we could try to do that. One example is have cycles of, for example, freeze and thaw, but that would include much more interaction with the system. And one of the attempts was actually our last chapter, where we tried if the replication of building peptidic oligomers within vesicles would initiate their growth. So that was one of the strategies we thought of.
Okay, so that satisfies the answer. Is there still time?
For a short question, yes.
So in one of your propositions, and I don't know which one, proposition 6, can one of the panelists read it?
Experiments on a time scale of weeks or months seem to be very convenient during the course of a PhD. This suddenly changes when the last experiments need to be done to finish a chapter or publication.
So here you describe one of the challenges, which is the long time period to get structures, to get oxidation, and to get final establishment of the library. And in this case, you predominantly rely on oxygen, right, to oxidize the library. And I was wondering, because the reaction has to take place in the inner core of the micelles. Have you ever considered taking hydrophobic disulfides at these two reactions, which gonna go into the core and then speed up the reaction of at least disulfide formation? There are some reagents that you can envision of, right? So pyridine, 2-mercaptopyridine, the disulfide of that one, should allow disulfide formation and maybe speed up the reactions. Of course, it's gonna change the equilibrium maybe, but it at least helps you solve that one problem, which is at the end of your thesis, you're still waiting for the results.
That is indeed one of the ways we could do that, but there is already an established methodology that we use in the group, is by oxidizing our mixtures with a solution of sodium perborate. And in this case, we have much faster oxidation, so we immediately get to the composition of the library where we form already disulfide, so we don't have to wait for the lengthy process of oxidation.
Thank you for the answer.
Thank you very much. And I give the word to the promoter, Professor Otto.
Dank u wel, meneer de rector. Meneer de promovendus, we've of course already discussed many times and many things, many details about this thesis, so my questions are going to be a little bit less detailed now, and a little bit more coarse-grained. And following on from the previous opposition, of course you've pursued a few strategies aiming at combining autocatalysis and vesicle formation. So far they haven't been successful. But if I were to give you another 4 years, what would you embark on? So that would give you the opportunity to completely even abandon this system and maybe think of some completely different strategy. What's your thought?
Hooggeachte promoteur, thank you very much for your kind words and nice question. And that was actually one of the questions I was hoping not to get because it's a very hard one. And yeah, so how to achieve what I have not been able to achieve in the last 4 years, I'm not quite sure, but starting from the thesis itself, there is few strategies we could follow, so changing structures or conditions, but this is again more exploratory approach and not really very focused strategy to go towards that. But maybe one of the options would be to optimize conditions in which we form vesicular structures themselves, and then include different self-replicating molecules that contain information within them.
Okay, thank you.
Thank you very much. De commissie zal zich enige ogenblikken terugtrekken voor beraad. Meneer de promovendus, het college voor promoties deze universiteit, door ons vertegenwoordigd, na kennis te hebben genomen van uw proefschrift met bijgevoegde stellingen en deze door u te hebben horen verdedigen, heeft besloten u het door u begeerde doctoraat aan de Rijksuniversiteit Groningen te verlenen. Uw promotor, de hoogleraar Otto, is gemachtigd u op de gebruikelijke wijze met deze waardigheid te bekleden.
Volgaarne aanvaard ik de taak mij door de rector opgedragen. Doch alvorens deze uit te voeren wil ik graag enige persoonlijke woorden tot u richten. Dear Boris, so in a few moments you'll be Dr. Bartolec, and with that a phase in your life is coming to an end, and a new one is about to unfold. It's a good moment to look back on the past period, and your adventure as a PhD student in the Netherlands started on the 3rd of August 2012, when you wrote to me about the possibility of doing a PhD in our group. Now, as it happened, the 3rd of August is my birthday, and receiving an email from a good student who wants to do a PhD in your group is indeed a very nice birthday present. So you knew about this position from Ivica Tritila, countryman of yours who joined the group somewhat previously, and your background in organic chemistry and your genuine interest in supramolecular chemistry made you a strong candidate, and I was very glad that I could hire you. You then joined the group in November that year, and you inherited a project that was started by Wietse Smit during his undergraduate research, and was then further developed by Jan-Wei Lee, a PhD student who finished not too long after you started. So the results that Jan-Wei and Wietse had obtained suggested we should be able to create compartments or vesicles from these dynamic molecular networks. The idea was that the process of compartment formation would actually drive the synthesis of the very molecules that make the compartments in an autocatalytic way, in analogy to what we had observed before with fiber-like systems. So while it appeared that you jumped into already up and running and pretty well-developed projects, it turned out, as quite often happens at the forefront of science, that things are not that simple. So the synthesis, to start with, of the lead compounds, the lead structure was not very well developed, and it took quite a while before it was possible to obtain it in decent quantities and with decent purity. After cracking that problem, another one was already waiting for you, because it turned out the analytical method that was used before was also only giving a partial picture of the system, and once you developed a much better improved method, it became obvious that what looked like a promising system wasn't so promising at all. So after a lot of work and after a lot of problem solving, it looked we had just only gone backward. And now many people in that position would have despaired, and perhaps you also did, but somehow you never showed it, and it didn't appear to impact on your work. You just kept going. And at that stage, there was only one hint left in the work of your predecessors that was worth pursuing, and this was the observation that the aggregates were somewhere halfway to the formation of vesicles. And I think it's indicative of your strength of character and that you persisted in working towards the goal of your project under the circumstances in which many others probably would have been thrown in the towel and changed projects. But instead, you redoubled your efforts, and from that moment, things really started to work, and nice results started coming out. So your strategy was to explore very many different conditions. We heard about this, temperature, co-solvent, in the hope that these would favor the formation of compartments, and your efforts indeed paid off. And you identified the conditions where indeed it's reliably you observe the vesicles that we were after. And the back cover of your thesis nicely shows that you identified indeed also a whole range of other characteristics, assemblies with rather unexpected morphologies along the way. So you worked on many approaches at the same time, and you also found conditions under which autocatalytic formation of structures occurred. But as you explained, much to our frustration, whenever autocatalysis happened, there were no vesicles. Whenever vesicles were there, there was no autocatalysis. Thus it appears that these things are mutually exclusive. And in hindsight, that probably makes sense, because autocatalysis requires edges to grow and vesicles don't have edges. Thus I think overall you achieved the maximum out of the system that it actually had in it. And you did this mostly by yourself. So most of the time you were the only person working on this project, perhaps only with the exception of chapter 4, we had some help from me, Chen Yan, who did his bachelor project under your guidance. So I'm pretty sure that you wouldn't have come as far as you did without a great deal of persistence and courage. You also fulfilled an important role in the group, beyond your own project, doing more than your share of the communal duties, always involved with the running with affairs of the group at large. And also not unimportant, you were a very pleasant person to have around, interact with, and socialize a great deal with the people in the group and beyond, to the point that in your acknowledgements you even claim the partial ownership of the word bottle. So now we're approaching the moment that you will finally become doctor. A very nice moment for you and for your family who's traveled all the way from Croatia to here to witness this. But before we go there, there are some people that I'd like to thank first. First of all, members of the reading committee, so Professor Peter Walde. So thank you very much for coming all the way from Zurich to here and for reading the thesis, providing comments. I'm also very grateful to Professor Ravo and Rufus, who unfortunately could not be present here for their involvement in the reading committee. I should also thank a lot Mark Stewart, who is here in the opposition, for his invaluable assistance with electron microscopy. I think the thesis would not be close to where it is now if it hadn't been for Mark's role and help and support in this. And then we're also very grateful for the support on the technical front from the people that keep our mass spectrometers and HPLCs and UPLCs up and running. So Theodora Tiemersma, Peter van der Meulen for the NMR support, and Monique Smit help has been really indispensable. So let me now continue with the formal part of the ceremony. So can I please invite you to stand up? Uit kracht van de bevoegdheid ons bij de wet toegekend, volgens het besluit van het College voor Promoties van deze universiteit, verklaar ik, Sibren Otto, u, Boris Bartolets, te bevorderen tot dokter en u alle rechten te verlenen die door wet of gewoonte aan het doctoraat aan de Universiteit van Groningen zijn verbonden. Belooft u als dokter in de toekomst te handelen naar de Nederlandse gedragscode wetenschapsbeoefening? Kunt u plaatsnemen. Nadat ik alzo de mij opgelegde taak heb volbracht, mag ik de eerste zijn die u met deze promotie geluk wens en als dokter begroet.
Ten bewijze deze promotie overhandig ik u het diploma, ondertekend door rector magnificus, secretaris en promotor en voorzien van het grootzegel van deze universiteit. Doch, alvorens daartoe over te gaan, zeer geleerde heer, kwijt ik mij van een aangename plicht om u, ook namens het College voor Promoties, met deze verworven graad geluk te wensen. En hiermee verklaar ik deze plechtigheid voor geëindigd.